We got a sunny Wednesday. I think it's supposed to actually warm up. So we might have a couple nice days weather to look forward to. We're talking about line integrals. We talked about line integrals yesterday as generalizing the definite integral defined on an interval. We're now looking at the definite integral defined on another one-dimensional shape, namely a curve either in the plane or in space. So we talked about lateral surface area. We talked about average value. But, the superstar application of this is work and circulation. So we're going to talk about that today, and then we'll talk about a related quantity called flux. But here's the setup. We talked about work actually at the beginning of the semester when we talked about dot product. Work is sort of defined as force through a distance. And if we had a constant force and we were moving it across along a vector PQ. Oh, I'm muted. All right, thank you. Okay, so let's try that again. So yesterday we started talking about line integrals, right? Generalizing the one-dimensional definite integral. And we looked at certain applications, lateral surface area, average value. And today we're going to look at ostensibly the most important application of the line integral, which is work. Now, we talked about work at the beginning of the semester. Work is force times distance. So if you have a constant force and you want to move something along the vector PQ, so we're starting here at P and ending up at Q. We're going to move it from P to Q. Then the work done was we would take the dot product, F dot, and let's say the force is acting this way. So let's say it's like gravity or something. Right? We had to figure out how much force was in the direction of the motion. So we had a dot product F dot PQ hat times the magnitude of PQ. And when you went through and worked that out, we ended up getting work is F dot the vector PQ because the magnitudes canceled out. But this was kind of how we arrived at that. So the key takeaways here, if we have a constant force, then we need to figure out how much force is in the direction of the motion. To get the direction of the motion, we take the unit vector associated with that to figure out the direction. F dot, that unit vector, gives you how much force is in that direction, and then we multiply it by the distance we're moving it. Does this all ring a bell? This goes back to dot product, which I think that was like the end of the first week of class. So we're going back like 11 weeks on this. So one of the properties of work is that it's additive. In other words, if you're trying to figure out the work done, that's what we ended up with, Zoran. This was kind of our final thing, but this is how we got to that, and this is the piece of it we're going to be using today. Okay. Yeah. So this was the final thing we got, but this is how we set it up. Yeah. So the one thing about work is that it's additive, which means if you're trying to figure out the work moving from P to Q, you can chop this up and you can look at the work going each thing along the way. So it's an additive quantity, which means it's the perfect kind of quantity we can use with an integral because it's additive. So here's the setup. Suppose you got a curve C and it's parameterized by R of t. And not only is R of t smooth, let's assume that the principal unit tangent vector, this is the direction of the motion. So there's a couple different ways you could frame that. Right? It's the direction of the motion. if you've got your R moving along here with this orientation, so this is the curve C, then your t hat is the direction you're going. Right? In other words, if whatever force is keeping you on this trajectory suddenly disappeared, you would be spinning off in the t hat direction. Okay? That's our principal unit tangent vector. So let's assume that we've got the curve C parameterized in such a way that the t hat is continuous. Right? So suppose that the t hat is continuous. And let's suppose that we're moving through a vector field F. And we'll stick to, we can do 3 dimensions. We can always reduce it to 2 if it needs be. Let's say this is a continuous vector field. What do we mean by continuous vector field? Well, we'll just say the components are all continuous. Right? Continuity of vector value functions means each component's continuous, so that's the same thing that's happening here. Right. So let's say we're trying to figure out the work done moving along C with this parameterization. So we're going to move along the curve C through this vector field. Okay? So we're trying to figure out the work. So what we can do is we can go in here and we can chop stuff up because work is additive. So I'm going to go in here, I'm going to chop the curve up into a little tiny piece. Right? And we're going to let W sub I be the work done moving along the ith piece. Right? That's going to be W sub I. So since work is additive, the work done moving along the curve here, that's just going to be the sum of all these little W sub I. So you move it a little bit, move it a little bit, move it a little bit, add them all up. So the total work done would be the sum, I goes from 1 to n, of W sub I. So let's take a look at this W sub I. So let's say we got this little piece here. So we're looking at one little piece, like that. And so to get the work done here, I would need to take the force times the direction. So how much force is in the direction of the motion, times the distance here, times the length. Now the length of that piece, that's what we're calling our arc length, delta S sub I. So how much force is in the direction of the motion times delta SI. And if we assume that the delta SI is very small, whoops, not norm. So if we assume that if the delta SI is small, we can take the force over the entire little interval here to be the force at, like, you know, one of the endpoints. So let's say this is at the point x sub I, y sub I, z sub I. So if this is small, since the field is continuous, then we're going to approximate the field throughout the entire segment to be the field at just one of the endpoints. Right? And that's continuity. Continuity says close inputs give you close output. So if I have a very, very tiny piece, the force isn't going to vary much over that piece. Does that make sense? And since t hat's continuous, we can also approximate the t hat there as well. So once again, if t hat's continuous, the direction's not going to vary that much over a very tiny piece. And so what this does is this sets up a Riemann sum. So the work, which would be the actual sum of these little bits of work, would be approximately equal to the sum. I goes from 1 to n, f at x sub I, y sub I, z sub I, dot t hat at x sub I, y sub I, z sub I, delta si. So once again, I've run out of room here. I'll just start way over here, because this is an approximation. It's an approximation that will get will turn into an equal sign at the limit. Okay, and now I'll take a limit of this as the norm of the partition goes to 0. So that means we're chopping this curve up into smaller and smaller pieces. Since f and t are continuous, we would get the work is the integral over c f dot t hat ds, which is our line integral. Okay. So once again, the way you want to read this integral is we're looking at how much force is in the direction of the motion. That's f dot t hat. And we're taking that times the little infinitesimal distance it's moving along the curve, and then we're adding all those pieces up. Okay, so that's our work integral. Now, if we've got this parameterization available to us, then we know what t hat's going to be. T hat is r prime of t over the magnitude r prime of t, and we know what the arc length differential looks like. So we talked about this yesterday, r prime of t dt. That's a callback to chapter 13. So if I look at the integrand f dot t hat ds, if I cast f as a function of t via the parameterization, and we'll talk about this here in a minute, then this would be f dot r prime of t over the magnitude r prime of t. And then the ds is magnitude r prime of t dt. What do we know about dot products? So we've got this property of dot products. If you have v dot w times a scalar k, yeah, I can move that scalar. The scalar floats thin there however you want. So what I can do is I can take this scalar, because it's a magnitude, and I can float it in, and that's going to cancel out this magnitude down here. So the long and short of it is, if you take the f dot t hat ds, that's just going to be f of t dot r prime of t dt, and oftentimes this is written as f dot dr. Okay, so oftentimes you'll see work as the integral over c of f dot dr. And so this kind of gets back to what you asked about, Zoran. When you compare the two formulas, you know, how we got the formula versus the formula we used, this is the exact same type of thing. So the work that we had developed, f dot pq hat, magnitude of pq, that's analogous to work is the integral over c f dot t hat ds. But once you go through and simplify, work is force f dot pq, that's then f dot dr. Right? So hopefully when you go back and review what we did today, you can go through this and see how this integral gets built. Because when you're off in the wild doing, you know, in your other engineering classes, physics classes, or whatever, and they're throwing integrals at you, it's always good practice to look at the integral and see if you can figure out what it's calculating, either from a derivation standpoint or by looking at the integral itself. Look at the integrand. What's the integrand doing? What are you adding up? Okay. All right, example 5. Find the work done moving a particle through the field f of x, y, z along the line segment starting at P and ending at Q. And then what happens if we go the other way around? All right. So once again, the goal here with these, remember, work integrals are just special types of line integrals. So to evaluate the work integral, we're going to use the same strategies we talked about yesterday. Namely, we want to get the work integral in terms of just one variable. So oftentimes, if we're not given any particular function here, we're going to default and do a parameterization. We know how to get a parameterization of a line segment. If you forget how that's done, we're going to see how it's done again right now. And so that's going to be our goal here. Is our first step is we're going to parameterize the line segment. From P to Q. That's going to be our R of t. Second, we're going to get our vector field, which is given to us in terms of f of x, y, z, in terms of just t. 3, we're going to calculate then f dot r prime of t. And then 4, we're going to integrate f dot r prime of t dt. I should put an f of t here just to be pedantic. So those would be the steps. So it's very easy. It's the end of the semester. You got all kinds of other stuff going on. It's very easy to get lost with these problems. So I'm trying to lay it out as best as I can. So let's talk about parametric line segments. So remember how you get the parametric line segment. X equals, you start off at your x naught, whatever your x naught is, plus your change in x times t. Y is y naught plus your change in x, a change in y times t. And z is z naught plus your change in z times t. And then to trace out the segment that starts at P and ends at Q, t just has to run from 0 to 1. You're starting at x naught, y naught, z naught, and you're going to end up one unit of delta x, delta y, delta z later. And so they tell us here the point P we're going to start at negative 1, 0, 3. And then we're going to go to Q, 3, negative 2, 4. So let's go ahead and calculate the delta, all the deltas here. Well, I guess we should do this first, the x naught, y naught, z naught. So we're starting here and we're ending here. So we're starting at the point P. So this is our x naught, y naught, and z naught are those three things. And now let's compute the delta x. So I'm starting at negative 1, ending at 3. So to get delta x, I take 3 minus negative 1. So my delta x is going to be 4. Delta y, we going to end up at negative 2. We started at 0. That's our negative 2. And then our delta z, ending at 4, started at 3. 4 minus 3 is 1. Yep. Okay. So now I just plug that in. So my R of t here is x naught plus delta xt. So minus 1 plus 4t why not 0 plus negative 2t, so just negative 2t, 3 plus 1t, 3 plus t, and this is good for t between 0 and 1. And we could check this, right? If we plug in t equals 0, all of these things drop out, and we're left with negative 1, 0, 3, which is our original point P. And if I plug in t equals 1, I've gone 1 unit of delta x, delta y, delta z. I plug in t equals 1, negative 1 plus 4 gets me to 3. We get to negative 2, we get to 4, which is exactly what we have here. All right? So do you remember how to set up line segments? Those are common things. Line segments, and then yesterday we also reviewed the parts of circles. So once again, those basic parametric things we talked about back in the day. So that's our r of t, so that's step 1. Now step 2, we need to get our function f, or our field f rather, which is a function of x, y, and z as a function of t. And the way we do that is on the curve, on this line segment, I have x, y, and z as functions of t. So once again, the line segment this way is packaged parametric. So on the line here, on the line segment, x is given by negative 1 plus 4t, y is given negative 2t, z is given by 3 plus t. So to get my f of t, I'm going to plug in x as this, y as this, and z as that. All right. So go to my field. My field is yz x squared xz. So it's yz x squared xz. So y times z, y is negative 2t, z is 3 plus t. So this first quantity here, negative 2t, 3 plus t, comma x squared, negative 1 plus 4t squared, and then xz minus 1 plus 4t times 3 plus t. Okay? And that would be our f of t. I don't know. If you want to multiply this out, we would have negative 6t minus 2t squared. When you multiply this out, don't forget your middle term. And then here you got your minus 3 plus what? 12t minus t plus 11t plus 4t squared. Okay. So once again, this is function composition at its finest. The field f is a function of your position in space, x, y, and z. Your position in space is a function of t. And so now we have the field f. You plug in a t between 0 and 1. That gives you the location x, y, and z on the line. And then this is going to be the field on the line. So now I need to take f dot r prime. So for that, I need what r prime of t is. So I need to take the derivative with respect to t of r of t. And how do I take the derivative of a vector valued function? Yep, component-wise. So the derivative of the x component here with respect to t, that's just going to give me what? 4. And then I'm going to get -2, and then I'm going to get 1. All right, so no big surprise here. It's a line. The derivative of that linear function is just going to be the delta x, delta y, delta z. Okay, so there it is. So then I would compute f dot r prime of t. So we'll do that. It'll remind us how to do dot products. So I got to get the f in there. Minus 6t minus 2t squared. One minus 8t plus 16t squared. Minus 3 plus 11t plus 4t squared. Dotted with, that looks like a 9. That's going to mess me up. That's a 4t squared. Dotted with 4, -2, 1. So, yep, Zoran's right. So what we do is we're going to multiply the corresponding components. Then add them up. So I'm going to have 4 times -6t minus 2t squared plus -2 times 1 minus 8t plus 16t squared plus 1 times minus 3 plus 11t plus 4t squared. And that'll equal whatever it equals. Okay, I don't want to go through all the arithmetic here. And then finally, step 4, we would integrate. And how do I find the bounds on the integral? Well, the r of t, when we did it, that line segment, t was between 0 and 1. So you'd integrate 0 to 1. F of t dot r prime of t dt. And then you would get your answer. So I'll leave you to fill in those details. You get -31 halves. All right. Now, the fact that your work is negative what does that mean? Is overall, in general, right? Like, so the net effect. Are you traveling with the force or against the force if the work ends up being negative? In general, overall, net effect. If your work's negative, are you moving with the field or against it? And how can you tell? So let's look at the integral here. The ds, remember, that's your arc length differential. This is always going to be what kind of number, ds? It's an arc length, so ds is always going to be what kind of number? So ds is going to be a what? This is a length. Well, just what kind of scalar, though? What's the sign? It's always going to be a positive number, okay? So if my work ends up being negative, then that means this is where the negative is coming from. So if I'm getting negatives out of this, and once again, it's not negative all the time. It's just there's more negatives than positives, right? It's a net effect. Then if the dot product f dot t hat is more negative than it is positive, then that tells you that you're moving how? Are you moving overall with the field or against it if the dot product's negative? Yeah, it's against, right? Remember dot product is, like here's your T hat and here comes your force field. Right? That's telling you that if the dot product's positive, you're going sort of in the same direction. This would be an F dot T positive situation. But if it's negative, this would be an F dot T hat less than 0. So positive dot products, you're going more or less in the same direction. Negative dot products, you're going more or less in the opposite direction. And that comes from this little gem. That's going to be a 1 because that's a unit vector, but that has to do with that theta. Okay, so once again, properties of dot product help us understand what's going on here. Now, what if I decided to go from Q to P? So I went from P to Q. What if I turned around and went from Q to P? What would be the only difference? I've got my T hat here. How would the T hat here relate to the T hat here? I'd still have the same arc length differential. I'd still have the same field F, but that my T hat would be the exact what? Exact opposite, right? So I'd have this would be like minus T hat here. Whoops. And so what can you do with negatives here? That negative is really a -1. So I can move that out of the dot product and move that out of the integral. And so if you reverse the direction on your curve C, you're just going to get the exact opposite. Does that make sense or not? So if going, it's like if you're going uphill, you're working against gravity. And then if you turn around and come down the same path, you're going with gravity. It's the exact opposite. So if we kind of use this notation, if minus C denotes the curve C with opposite direction, then the work done, the integral minus C F dot dr is going to be minus the integral over C F dot dr. Okay. All right. A related quantity to work is circulation. If you have a simple closed curve and your field F is a velocity flow field, then the circulation of F along C is given this way. Now you notice there's that little circle there. So that circle there indicates that you got a closed curve. Right? And we're going to stick to simple closed curves. So these are closed curves that do not intersect themselves. So I think, Zoran, you might have asked about this yesterday. So here we're specifying a simple closed curve. So the point is, this is just another way to interpret the work because you're looking at the flow along C. Right? So flow along in the same direction of, we use the dot product for that. So find the circulation of the field 2y negative x once around the unit circle counterclockwise. Okay, so once again, we're going to use parameterizations here. So we're going to figure out our r of t, and then we're going to figure out our field f of xy as a function of t. We'll compute the dot product f of t dot r prime of t, and then we'll integrate. So step 1, unit circle. What's the parameterization for that? This is literally the definition of sine and cosine, isn't it? X is the cosine of t, y is the sine of t. Now remember, they want this parameterized. We do have to be a little careful. They want it parameterized counterclockwise. So counterclockwise, x is cosine, y is sine. And to go once around the circle, t runs between what two values? Yeah, 0 and 2 pi. Okay. So that's our r of t. Cosine t, sine t. All right. All right, 2 now, we need our field. Now we just got a two-dimensional field here. It's 2y comma negative x. And so to get the field as a function of t, along the unit circle, I know that x is cosine of t, y is sine of t. So 2y would be 2 sine of t. And then minus x would be minus cosine t. So now I'm going to take f of t dot r prime of t. So that's 2 sine of t times negative cosine t dotted with the derivative of r of t. Derivative of cosine is? Derivative of sine is? There it is. And once again, how do you take the dot products? Multiply corresponding components. Add them up. Yep, very good. Okay, so you've got negative 2 sine of t cosine of t. I'm sorry, I screwed that up. Hold on. I multiplied the wrong things. So 2 sine of t times negative sine of t. Yeah, that's your negative 2 sine squared of t minus cosine squared of t. Now, there's an opportunity to simplify this a little bit with Pythagorean magic. I could split this off. Minus sine squared of t. Yeah, minus sine squared of t plus cosine squared of t. So you can use Pythagorean magic as much as you can. And we get down to this integral. There it is. Now we go through and integrate that. So the circulation here, the integral along C, f dot dr. In this case, the parameterization, the unit circle, we're running from 0 to 2 pi minus sine squared of t minus 1 dt. We can split this integral up. And we won't go through the details, but how would you attack that one? What would be your process to figure that out? If you had to integrate that. Yeah, yeah. So you do your reduction with your cosine 2x. Okay. This cosine piece would drop out because you're integrating 2 complete cycles of that cosine curve, but you would get whatever answer you get. So I'll let you do those details. Negative 3 pi. Okay. So once again, This circulation, are we going with the field or against it? Yeah, and so and on your take home, there's a the take home has flux, which we'll talk about flux here in just a second. I think it's instructive to, especially in these two-dimensional ones, you've got these tools, even with the 3 dimensions, but it's a little harder to do. So that's your field, and we're doing the unit circle counterclockwise. So if you think about it, the unit circle counterclockwise goes this away, and you can see you're pushing against the field all the time. You follow? So negative work means you're putting work into the system. You're working against the field. Positive work, the field is doing the work for you. All right? I'm not quite sure if that's the same convention they have in physics or not, but there it is. Okay, let's talk about flux. So work, circulation, both involve moving along with the field. How much of the force is in the direction of motion? So if you have a simple closed curve C, like that, then a simple closed curve in the plane bounds a region. And so we have another concept we're interested in called flux. And whereas circulation and work, you're moving along the curve, so you're looking at dotting it with a tangent vector. How much are you picking up as you go along the curve? Flux is talking about going across the curve. So for example, outward flux. How much stuff is escaping? Okay, so I don't know, like in like biology, they have like osmosis, moving things across membranes. So you could have like outward flux or inward flux. Exactly, electricity and magnetism. Yep, and that's how we're going to end the course, Zoran. Surface integrals are like the second to last thing we talk about before we talk about the big theorems. Yeah. Oh, no, you'll get there. Yeah, this is a showstopper. And hopefully you've noticed already, think about all the stuff we've done we've just taken our first steps into chapter 17, and look at all the stuff we've reviewed already. Right? It's great. Okay, now so for flux, if we want to know how much is going across, it's not the tangent vector we're interested in, but it would be the what? The normal vector. How much is getting directly across? We want the normal vector. Okay? So flux is going to be the integral over C of f dot n hat ds, or f dot dn, all right, depending on how you see it. And let's talk about what that would look like. And so once again, we're looking at two-dimensional flux here. As Zoran mentioned, for three-dimensional flux, we need to go up and talk about surfaces. But here's the idea. Let's say you've got this. Let's say you've got your curve oriented counterclockwise here, and you got your, let's say your t hat is your x comma y. All right, let's say that's your t hat. Then for your n hat, you would have two options, because since it's two-dimensional, remember this little trick? You reverse the components and make one of them negative. So either yx or y minus x would be your choices for n hat. So if I think about t hat, like in this particular scenario, the x would be negative, but the y would be positive. So, let's look at N1, N2. For N2 here, I would want the x and y to both be positive. So I'd have the y comma minus x for this one. And here x and y would both be negative. So I'd have minus y comma x for that one. So this would be your inward pointing normal, and this would be your outward pointing normal. Okay, so this would be your inward, and this would be your outward. Okay. And so once again, if taking it back to r there, and we sort of divide out that magnitude, notice that when we go through and normalize things, this is the same. So the magnitude of these normal vectors is the same as the magnitude of the tangent vector. And so we get the same cancellation we had before. So when you do the n hat ds, you're going to get the, or f dot, I should say, you're going to get cancellation here just like you did before. And so it's going to reduce down to this formula. So the same kind of thing happens. All right, so these are your formulas here for flux. And once again, flux is directional, just like work. So if you have inward flux, outward flux, they're just going to be opposites of each other. But here's the formula here. If you've got a simple closed curve, if C is oriented counterclockwise, then this would be the outward flux. You know, and why is there a tendency to just look at outward? Well, we'll talk about more of that later. You give it by this formula. So instead of taking your field dot x prime comma y prime, you're taking the field dot y comma minus x because of this picture here. Right? All right, so we don't have time to finish this example today, but just to kind of set it up for you here, we'll finish up and do the flux integral next time. But we've got a triangle with these vertices. So there's one like this on your take-home, so we'll do this tomorrow. And this is going to be oriented counterclockwise, so it'll look like this. And we've got our field. So tomorrow we're going to go around and figure out what the total flux is, outward flux is across this triangle. So we'll be breaking up into 3 parts. And then we'll talk about the differential forms of the line integral. Yeah, you break it into 3. Yep, a flux for each side. So we'll finish that up tomorrow. And then on Friday, we're going to talk about, we'll start talking about conservative vector fields. Conservative vector fields are vector fields that are gradient fields. All right, conservative vector fields are gradient fields. Yeah. So we'll talk about that on Friday. And we'll just keep on marching through. As always, folks, I appreciate you tuning in today. Have a great rest of your day, and we'll see you tomorrow.